Welcome to the 2021 webinar series for SLCAN. We have a wonderful selection of presentations coming up for us in the next couple of months, and we have the pleasure of having Joel as being our first here. Joel is the Principal and Sustainability Practice Area Leader with RWDI, where he is a trusted advisor on projects aiming to create comfortable, sustainable built environments that harness a site's natural energy resources. Joel specializes in energy and daylight modeling, solar and reflected light studies, thermal and visual comfort, and net zero strategies. Joel is a passive house certified consultant and a WELL faculty member and performance testing agent. With that, we're going to hand this over to Joel and let him start his presentation.
Great, yeah, thanks very much. And yeah, thank you for having me here today. I'm happy to be speaking with you all and your group, who we've done a lot of work with, and happy to continue to participate with. Yeah, welcome everyone. I guess I'll leave my video on while I do this, but hopefully you're able to see my screen and video as well. So I'm going to be speaking to you today about work we've done at the University of Toronto recently. It's a Target 2030 is the title, establishing utility performance targets for carbon reduction at the university. So this is a project that we worked on with the U of T Sustainability Operations and Services. And yeah, I'm happy to share this work with you today. I'm also very fortunate here to work with a very bright and talented team at RWDI in our sustainability and energy groups. And this by no means is my work alone that I'm going to be presenting to you today. So I'd like to also acknowledge Sebastian Carrizo, Jennifer Harmer, Sandra Tedesco, and Mike Williams, who have all played a big role in this work as well. So a big thank you to them, and I'm happy though to share it with all of you. So just I guess maybe a little touch of housekeeping. What we'll do if I'm going to run through the presentation. I think it's going to be about 40 minutes maybe. And so then if there are any questions, please feel free to drop them into the chat box as we go. I'll like was mentioned, we'll leave you on mute during the conversation. I guess it's not a conversation if it's just me, but we'll leave you on mute, and then you can either type in questions to the chat box, or I'll unmute you at the end of the talk, and there should be 15 minutes or so available for us all to discuss this work or any other questions you might have. So, okay, let's get started. So, a couple of the learning objectives of this talk today. We're going to be, or I'm going to be speaking about the comparing and contrasting different building energy performance targets. So how that applies to lab spaces. Number two, we're going to summarize the development process that we followed for the U of T Tri-Campus Utility Performance Standard. So we'll talk about how the kind of the nuts and bolts of how we put together the performance standard and what went into the decision making. So key considerations when developing targets for wet and dry lab academic building types. So I'm going to talk about that too. So really this was a big process, a long process of collaboration with the university. And so as much as as we'll talk about, you know, the final kind of decisions that were made and some of the targets that were set, we're also I'm going to talk about the process too, so that you know, my fourth point, which is identifying lessons learned and considerations for other academic and research facilities that are seeking to improve utility performance through a similar framework. So that's the idea, is that I'll show you the process and show you where we ended up, and then hopefully it's kind of something that can be repeated and shared. So as I mentioned, this was a project that our team worked with the University of Toronto. The sustainability standard needed an update. You can see there's a version of the 2019 reference guide there. The standard is meant to govern all new buildings and major retrofits on the campus. The standard was meant to govern all three main campuses of the U of T. So there's a Mississauga, Scarborough, and then the St. George campus. And it's also meant to consider future growth. So across the three U of T campuses between now and 2030, there are plans to construct over 670,000 square meters of new gross floor area. So we didn't want to just come up with a plan that would work for the current state of affairs. We needed, for the forecasting of our energy and carbon work, we needed to consider this future growth, which was an important piece of this as well. So here's some of the key objectives that we started out with for the standard. So number one, we needed to support the University of Toronto's big, hairy, audacious goal, the BHAG, which was a 37% GHG reduction by 2030. So about 10 years out from when we started this project, we would need to come up with a 37% GHG reduction from their 1990 baseline, and that's something that has as a target that's been set by their carbon plan. Number two, we needed to take a holistic approach to sustainability. So I'm going to be talking mostly about energy metrics today. That's kind of in my wheelhouse, and also just because of the nature of this talk and what we're focusing on, we'll focus mostly on that. But the standards do need to, and did consider not just energy, but comfort and water use and those as such. We needed a requirement for today and a roadmap forward, as I mentioned. Strengthen the U of T's leadership position. So the University of Toronto already has set some aggressive standards and has been a leader over the years when it comes to academic energy consumption and a portfolio of buildings. So we needed to maintain and strengthen that leadership position. We needed to align with federal, provincial, and municipal energy performance requirements. So probably many of you on the call know there's a number of different governing protocols that need to be applied when you build on the campus, starting at the campus level requirements and then working your way up. And so all of those have different energy targets, energy submission requirements, and so really trying to align those was also a key part of this. And to reach our number 6 key objective, which was that we needed to provide a clear direction to project managers and design teams. So we wanted this standard not to be another burdensome kind of hoop to jump through, but something that aligned and complemented already standard practice. The 7th one, understand and embrace U of T's unique challenges. Okay, so some of those challenges being that it's in an urban environment. There is access to district thermal energy systems. The Carbon Action Plan is increasing the use of geothermal and geo-exchange systems on campus. So we have a changing energy source that we're dealing with. And also maybe the most complicated part of it all is that we have, with the 3 campuses, with the size of the University of Toronto, there's a vast array of building topologies. So we're not talking about just lab buildings here, obviously. And we needed to govern both new and major retrofits. So it's not just for new construction, but also for the existing building stock. And I'll show you a little bit about that now. So here's a breakdown roughly of the archetypes by floor area that we're talking about across the campus. So you can see that we're predominantly in admin and academic buildings up to almost 600,000 square meters. But when you look at wet labs and dry labs, making up another almost the same amount, right? Or maybe even a little bit more, up to 600,000 square meters of existing lab space already on campus. So this is a highly focused research university, as many of you know, and as such, there's a lot of lab space. Here you can also see in red the future planning. So significant growth planned over the next 10 years, which is our target. Kind of target timeline was out to 2030, as I mentioned before. So big growth in academic wet labs and residences. So how do we get there? So it's like any journey, it's one foot in front of the other. So step by step. The first thing we wanted to do was establish some context and benchmarks to the energy. So like I mentioned, let's look around at what else we need to fulfill as far as federal, municipal, local requirements. and then come up with a set of goals that would meet, or a set of goals that would meet those, and metrics that would meet those overall goals that I just discussed with you. We wanted also to be very clear about investigating a set of performance pathways. So we don't want to just come up with some pie in the sky metrics, some that we have really no way of helping design teams achieve. So we wanted to come up with a series of performance pathways that would show a roadmap, basically, for design teams on how to achieve these goals. So we got very specific in that, and I'll share some of that work with you. Okay, so first of all, the context. So some governing codes, as I've mentioned, we have the local codes that do govern are the Toronto Green Building Standard. There's buildings on campus that are going after LEED requirements. So obviously there's energy requirements and credits available for LEED. There's on campus, there's also pursuit of the CAGBC's zero carbon standard. The National Energy Code for Buildings is referenced. There are examples now on campus of passive house design targets too. So, and ASHRAE obviously is woven into many of these different standards, including the Ontario Building Code too. So the SB 10 requirements as well. So no shortage of reference material when it comes to looking at what our energy targets are for the campus. So here's a kind of we tried to do, first of all, is to as a way of simplifying the process. We first needed it to get complicated. So what we did is we laid out the timelines of some of the different requirements at the different campuses. So you can see the City of Toronto requirements up on the top there. There's rezoning applications, SPA, the Toronto Green Standard, requirement at that stage. At the permit stage, you have to have an SB 10 model or compliance shown, as well as for occupancy. And so we aligned a lot of these different timelines for the different submissions, just to see, what it is that design teams are currently working towards, and what are their challenges, and then how we could line up and look for synergies across these to simplify the process when it came to our own energy requirements. I won't dwell too much on that. It's a bit of a tricky one to figure out. And then what we did is we set up, we tracked each standard and code and determined the applicability of it as a benchmark to the key goals and priorities of the standard. So if you see across the top of the screen there, those are those key goals that we came up with the stakeholders. So the GHG reduction, obviously the big one there, but also having alignment, leadership for the university. All those goals are along the top. And on the rows on the left-hand side show each of the different guidelines and standards that we looked at. I'm not sure if that's being cut off for you. It looks like it might be a little bit. Hopefully you can read that. So it was, like I mentioned, it was a collaborative and iterative process, and at the end of which we could start to see some of the qualitative connections across these existing guidance and our key priorities. So the green color here represents a good or a very strong relationship. So for example, when it comes to our GHG reduction goals, we can see that the Toronto Green Standard, some of the upper tiers, the CAGBC, zero carbon, obviously, and the Association for Advancements of Sustainability in Higher Education, the STARS program at the bottom, also show good alignment with our goals there. The yellow, I believe it might show up, kind of looks pale green yellow, would mean a kind of a weaker connection, with red being that there's no or little alignment between those two. So just by doing this kind of visual exercise through these stakeholder discussions, we were able to see which of these standards, and you can see that the CAGBC zero carbon standard has a lot of green along its row, that you can see there where there's a lot of strength in some of these standards that might govern the work we're doing. So some of the context of some of the findings of our context work was that no one standard accomplished all the key objectives, and surprise, surprise, or aligned accurately with building topologies. And this is obviously why we're all here today, as we know that labs are a tricky one when it comes to predicting and governing energy use. So There were relative comparison pathways, so i.e., standards that have an energy performance that's X% better than something else, some sort of baseline. We found that that led to comparison and quantification challenges when it came to, the different standards. So if on one standard or one requirement, you need to be X% better than 90.1, 2013, and another one, you need to be X% better than another standard. It becomes difficult aligning all your team's design goals if you're working towards those relative comparisons. So we decided it would be preferable, the design team decided to use absolute targets. This really set an ease of projection for a growing campus. It made it very clear what we needed to do. And we were able to balance and calculate growth and carbon reduction, and therefore able to set a plan. So absolute targets was something else. That was a finding out of our early context work. We also wanted to look at high performance from multiple angles, but as I mentioned, energy is the driving focus of this standard, and so as such, it took the energy metrics were really at the heart of our work. So why do we go to absolute targets? Well, there's a number of reasons. Other leading campuses and cities are moving to absolute targets. So this is a definite trend we're seeing in the market when it comes to high performance energy standards, and whether it's at a municipal or kind of a federal level, we're moving in that direction. But also when it comes to benchmarking, there's a lot of reasons why it makes a lot of sense too at a campus level. Absolute targets are more representative of actual energy performance, so rather than savings compared to a moving or abstract target. So it's very tangible. And also it puts design focus onto improving the proposed building instead of targeting reference standard loopholes or ways to discount the reference. And so what we're talking about there is it becomes a bit of a shell game where when you're looking at relative performance, you're not only looking at the pure performance of your building, but you're also looking at ways of adjusting the baselines or the comparison buildings in order to make that comparison look better. And so this absolute targets get rid of that sort of gaming, I guess, or loophole looking, and just allows the teams to focus strictly on the metrics and on the energy consumption. And the absolute targets are useful for forecasting building and campus-wide energy use. So particularly when we have a number of different space types and building topologies, like I mentioned, it was a wide range, which would all have varying reference buildings that would be created as a comparison. This way we can simplify the process by having absolute targets across the board for different building types, and therefore we can forecast with a lot more certainty. So why is a relative target challenging at high performance? So this is kind of the flip side of that. So so like I mentioned, the high performance proposed mechanical systems are compared to high performance reference systems. So things can show up on one project. So a VRF DOAS system can look 45% better than LEED reference building, but only result in a 15% cost reduction. So you really, when you're targeting LEED, which does refer to energy costs, it starts to complicate the issue, and the decisions aren't always being made for pure energy and carbon reasons. It's and there are obviously reasons why costs should be brought in, but we wanted these targets to focus specifically on energy and carbon goals. Otherwise, we weren't going to be able to make that 37% by 2030, which was really the ultimate target here. There's also limits on what energy conservation measures can be used for relative savings. So reducing domestic hot water usage is not an allowable conservation strategy. So when you're comparing against a reference building, the usage needs to be the same, or the way the building is used. So we also wanted to encourage the designers and the occupants and users of buildings to be able to incorporate reduction strategies too. And so we wanted those to be rewarded in the ultimate metrics too. no credit for Energy Star or high efficiency receptacle equipment. And as we know, and I'll show you a little bit later in some of our modeling results, that labs have a very high receptacle equipment loads. And so that was something we wanted to be able to also take credit for and show performance for. No credit for improved air tightness too when you do a comparison like that. That's often the reference building would be the same as the proposed building in those cases. So we wanted also airtight buildings to be rewarded as well. So the final one there is consideration of the building geometry. So when you create a reference building, you use the same shape of building. So you don't get benefit for choosing a building that's optimally oriented or optimally sized and geometry chosen to, for passive solar gains and that sort of thing. So we wanted also to take credit for that. So looking back at that early concept work, we came up with a series of target metrics, and the target metrics that we chose for energy, these are mandatory metrics. We also came up with a series of what we called reported values, which were set to better establish current practices and performance, but we're not meant to be mandatory yet. We just want to be tracking this information so that we can start to implement those in later stages. So the mandatory requirements were, there's some kind of common ones here that you'll recognize: the energy use intensity, the greenhouse gas intensity, the heating TEDI or thermal energy demand intensity, and then we also incorporated a cooling thermal energy demand intensity too. The reported values that we were tracking are the enclosure R value, so an overall R value including all thermal breaks, and a whole building air tightness. We really want to be pushing towards buildings, new construction in particular, to be building with a consideration for a tight envelope. And here's a quick look at what those metrics are like. We're not going to spend too much time. Hopefully you have an understanding of these, but basically the total energy use index, the TEUI, is the total site energy use over the floor area of the space. So it's kilowatt hours per square meter per year. Similarly, for the greenhouse gas index, it's the energy use times emissions factors based on what kind of energy or what kind of source energy we're talking about: electricity, natural gas, etc. And then the TEDI is the thermal energy demand index, is the summation of all the space and ventilation heating output. So just the heating requirements over the floor area. And then similarly, the cooling one is the ventilation cooling output over the modeled floor area. So those were our key metrics that were mandatory and targeted. So the next step was really establishing a baseline. So where are we starting here? Like I said, the goal of 37% reduction by 2030 was against a 1990 baseline. So we're fortunate, and the University of Toronto has been, as I said, is a leader in this field. So they've been tracking energy consumption for a long time now. So we had a lot of data to work with, including, here's a visualization of one of the campuses. I think this is, just the downtown campus. And what we saw is we have good energy information for our baseline years back to 1990 all the way up to current years. And so we're already seeing some of the this is tons of CO2 equivalent visualization. And you can see that there's a lot of big green dots there showing the amount of energy being used by academic and research buildings, which ultimately are mostly lab spaces. And you can see that there's some of the smaller uses are, in our, let's see here, some of maybe the yellow buildings, the administration buildings, are a little bit less of intensity, but also less size here too, as this doesn't break it out by square footage. So we had the starting point, or our baseline year, 1990. We have all the historical and current energy carbon performance of the campus, and we have a new construction goal set by the campus of 37% better. So we now know what we need to achieve, what we need to reduce. Here you can see new construction. There's no numbers here, obviously, but you can see like relative sizing. We can see a target EUI that we needed to get to, and we knew that there was a gap that we needed to reduce. But more most of the carbon is in the existing buildings. So the major renovations are important, especially at the St. George's campus, where we have a series of historic buildings that need to be turned into classrooms and even lab spaces. So the major renovation projects are far more complicated, since no two existing buildings on campus are identical, and each has its own distinct starting point, performance, age, improvements, and so forth. So accordingly, creating archetype models for major renovation projects would only provide a representative performance improvement of the existing buildings modeled. So, and not all existing buildings of that type. So we really tried to get a representation of that, though. So here are a series of models that we created to test our pathways to energy performance. We wanted to avoid using generic boxes in this exercise. So often when we're at this stage of kind of planning, you'll just start to use, basically cubes or simple box models as they're called. But we wanted to capture some of the nuances of functional buildings on the campus. So therefore, we went through and picked some average or kind of normal, typical styles of buildings on the campus and modeled those explicitly. So these buildings, the 6 archetypes you see here, each have a combination of uses similar to in real life. So there's no one building on campus that's just an admin building. They have other functions as well. Same with some of the lab buildings. There's always office space. There's always some other research work being done in them. And so we wanted to capture the kind of the nuances of that. And so we used real buildings. And so these, you might recognize some of these structures. So this is maybe a good point too to talk about the difference between just a nuance here between the lab buildings that we modeled. Wet labs are labs that have high air changes, basically are driven by air changes. So these are medicine, chemistry labs that have fume hoods and like I said, are driven by air change. Whereas the dry lab buildings are really driven by equipment loads. So these are engineering, computer science, that sort of a research lab, which are not so much driven by the air changes, more so by the electricity consumption. And here's some of the kind of early archetype decisions that we built into the models. So here you can see an example of the wet lab archetype. On the right, you can see the pie of the space breakdown, and this kind of shows you that even a wet lab building is a third laboratory space, 14% lab support, a bit of office, some multi-purpose, corridors, stairs, storage. So what we wanted to do here is to have like an honest representation of what we feel a lab building is and what they plan to be for the future. There's all sorts of, as many of you know, there's all sorts of flexibility in space design, and we wanted that to be represented in the models. And you can see here, I'm not going to go through every input we put in, and this isn't by any means all the input, but this was our first step at creating a baseline or typical University of Toronto wet lab. Pardon me. And here's an example of a dry lab building. So similarly, similar sort of breakdown into space types, perhaps, maybe a little bit more on the office side here, and but similar space usage, set points, and that sort of thing. So here is our first look at some energy output. So this was the first take at running each of those archetype models. You can see that the 2 labs I showed you are number 2 and 3 in the columns there, but we ran it for each of the building archetypes. And trying to come up with something that was roughly code compliant and still tracking our key metrics. So you can see there that we have our total EUI in bold. I'm not sure if my mouse shows up, but so we're starting to get EUI numbers for typical buildings, and you can see, as expected, some of our high air change spaces, like the wet lab, have high EUIs, and that's when you look at the energy performance. You can see that there's a lot of space heating required with those air changes, and a lot more fan power associated with those buildings too. So We also tracked, as well as the EUI, we were tracking the greenhouse gas intensity here, so using emission factors local to the campuses, and some of the TEDI heating and cooling as well. And here these were our voluntary metrics, but we wanted to make sure that we were capturing those too. So what we came up with was we now have the tools basically in place with these archetype models to forecast a plan. So as I showed you before, we knew where our baseline was. We know where we need to get to. And so it's just a matter of plotting the course. And so we wanted to set up a series of steps to get there. And so you can see the X, Y, and Z here, yellow, blue, and orange, are different kind of categorizations of design choices or retrofit choices for existing buildings. So we wanted to come up with a package of mitigation measures that would help us step towards that goal, that EUI goal. We packaged those as being a low kind of intensity retrofit, which might be an interior renovation, things like lighting changes, that sort of thing. A mid-level retrofit would be something that really got into tackling the HVAC and mechanical systems of a space. And then a high retrofit would be all those, but also one in which the envelope was also included. So we might be changing our values and window types and things like that. So we wanted to create these bundles of measures that were feasible for design teams to understand, and then we wanted to show that they would be able to meet our goals. And so here's kind of some of those packages in a little bit more detail. So a low interiors style, in bracketed in yellow there, would mean that we were looking at LED fixtures, occupancy and daylight sensors, high efficiency fixtures and equipment throughout, and low flow water fixtures. So that would be kind of a low impact design change. Whereas a mid-level design change would be something that maybe included water side economizers, electrically commutated pump motors, EC motors, HRV or energy recovery ventilators on the exhaust, variable frequency drives, DDC building controls, and perhaps VRF systems too. So that would be indicative of what a mid-level design retrofit or new construction kind of design package would look like. And as I mentioned, a high one would be improved wall R values, improving the glazing. So maybe going from double to double or maybe triple glazed envelope. And then also increasing air tightness too. So looking at really reducing the amount of air that's leaking out of a building and increasing or decreasing our air changes in the spaces too. So we then took our models, as you'd imagine, and implemented these ECM packages throughout. So here's a first pass at those target results. And you can see here that we have a starting point and then a target. And so we were able to compare to with this, we were now able to compare to other codes and look at how we were aligning with some of the TGS standard and the zero carbon standard and that sort of thing, and figure out how well our buildings with these new energy conservation measures were performing. As we all know, labs are unique, which is why obviously we're all here today trying to figure out ways of doing that. So this was really our struggle, was bringing down the energy consumption in our wet labs in particular, dry labs also. So that was really the struggle. But you can see when you look at the energy pie down here for a wet lab, for example, you can see that there's a big shift when we get into our instituting our energy conservation measures, and I'll talk a little bit more about that right now. So here, so this is what we learned about wet labs in this process, is that obviously outdoor air and receptacles are critical to this archetype. So in particular, the air changes. We can get to significant energy savings just with instituting night setbacks and DCV fume hood systems. So there are really the good news is that if you can tackle those air changes, you can make significant savings when it comes to energy for a wet lab. And you can see that kind of shift here in the energy pies where we go towards, you can see that it was the orange here is the equipment. So we were able to greatly reduce space heating from 35 to 27%. We're greatly similarly able to reduce cooling a bit. And as you do that, the hard one is the equipment load just doesn't change, and so it becomes a bigger part of this reduced pie here. And the other thing we learned about this is that envelope modification really makes virtually no impact on this archetype. So because it's so governed by air changes, changes to the envelope, looking at improved R values, really was a bit of a drop in the bucket when it came to trying to shift that, move that needle when it came to energy consumption of these spaces. Similarly for dry lab, so this one is equipment dominated even more so. You can see in the orange pieces of the pie here. But the cooling being more because of the higher internal loads here in these spaces. So receptacle is really critical to this archetype. Again, envelope modification makes virtually no impact. And you really only get to 34% energy savings with full ultra envelope suite of ECMs. So it really doesn't push that needle as far as it needs to go to incorporate those sorts of changes. So for these ones, we really need to start to tackle, we've instituted all these kind of mechanical and electrical lighting savings, but we really need to start to tackle that receptacle use. So now we were able to, because we have each of these energy targets and we've run through the models, we were able to compare now to some of these other codes and standards. So what we found is that the buildings like the admin academic buildings, so basically an office type, and the residential buildings, similar to the MERBs, align very well with a TGS Tier 3, which is, we wanted to get to at least a Tier 3 when it came to these guidelines. So we were happy with that. Our performance looked like we're getting there with these sorts of measures, these packages that were instituted. But we really had a lot of trouble when it came to trying to compare the labs and athletic buildings to any kind of TGS archetype. It just didn't exist. So we weren't able to get that kind of confidence that we had in those other building types, that we had really, we were really being successful at moving those to a high performance standard. So really the way to do that was to look at our overall goals in the space, and that's what I'll talk about here. So we'll spend a little bit of time on this. This was really we spent this, as we did, we spent a lot of time with this sort of a graphic. And really this is where we were able to see how well we were gonna get to that target. So that 1990 baseline for energy consumption, or sorry, this is in tons of equivalent CO2. So our projected GHG emissions. The 1990 levels were known, you can see on the left-hand side there. And the 37% reduction is the black dotted line that runs across below that. You can see we had already, the campus had already, even with the growth between 1990 and 2018, had already started the reduction process of GHGs. So they were on the right path, even with the growth, but not going to be at that kind of pace. They weren't going to be achieving the 37% reduction by 2030. So that's obviously why we came in to help set these metrics. If building as usual continued until 2030 with the increase in buildings square footage, we would see a rise in the GHG emissions up to 160,000. So if we didn't do anything and kept on building buildings as they were to basically code standard, we were going to see a significant rise over the next 10 years or so. But the LCAP, or the Low Carbon Action Plan at the campus, had already started to address some of this. And so with that, there are some sort of initiatives around I mentioned earlier, transferring to district energy systems and geo-exchange. So that would be a significant reduction to GHG emissions. So we had the advantage of being able to piggyback off of those decisions. There was also some recommendations there around this kind of gray, the other LCAP reductions, which would be things like solar energy. So there's going to be some renewable energy on campus, and other decisions like that that were going to help reduce our consumption down to, below those 2018 kind of standards, just by following those standards. So if we also instituted those new construction reductions that we talked about, so going to the low, medium, high mitigation measures on new construction, you can see we're dropping the amount of new construction consumption, and we could get down to like the 92,000 range by also looking at reducing future construction practices. So really what that told us at that point was, and we knew this all along, but we weren't going to get anywhere unless we really tackled existing buildings. And so that's what you're starting to see in the pillars next to this, is that with the low retrofit, so for all existing buildings, getting the what was considered the low package of design, which was basically interior retrofits, so lighting, that sort of thing, we would achieve, another 5,000 tons of equivalent CO2. To really get down below our target of 37% over 1990, we needed to be at least instituting a mid-level retrofit for existing buildings too. So that means the full suite of existing buildings needed to have at least a mid-level retrofit to achieve that. And so that was significant, and we know that that's not possible for all buildings. So what that really told us was that we were going to have, if we want to achieve that goal, we're going to have some buildings that have to do high retrofits, and meaning full envelope exchange, and some that would wouldn't be able to meet that kind of requirement. So this really helped us kind of lay out, what kind of what kind of mitigation measures were required, and to what amount of the building stock we needed to apply them. So this was a constantly evolving graphic that the team worked with often. So currently implementation is ongoing. The focus today on energy and carbon, which were significant, like I mentioned, but also we made water, waste, materials implementations too that went into the energy performance and modeling standard. The new construction was relatively straightforward. We could institute those using, very similar to existing code recommendations, but the existing building was more challenging. Our approach for that was to give two compliance pathways, both a minor renovation, so a tenant fit out, and a major renovation. And so for any retrofit deemed minor, it must meet the prescriptive requirements that were included in the code. And any major renovation must meet a % reduction based on what elements are being upgraded. So if low interior, mid, high envelope reductions. And so in order for to help the campus make those kind of decisions, we implemented what was called a project charter. And that was a way of, if an existing building was coming up for retrofit, it was a way of selecting the amount of energy reduction that was required in that retrofit. So based on the different space types of that existing building, we were able to, make the projections that matched the work we did with the energy models to come up with a targeted energy target for each building, which would be unique to that building based on its space usage. So whether it had, 20% office and 80% lab or whatever it was, there would be a set of targets that were unique to that building that would be used in this calculator or the project charter. So some of the challenges and lessons learned, consider buildings that exist. So using, really representative spaces. So moving towards flexible spaces is a trend at the campus. So we wanted to maintain that flexibility, but that makes it hard to set those targets. So we really need to play with multiple archetypes and blending them together to come up with really executable, I guess, plans when it comes to energy and carbon reduction. Particular focus on existing building upgrades. So that is the elephant in the room when it comes to energy consumption. And so that needed to be tackled and addressed really early. It's a significant contributor and trickier to assess. So definitely we spent a lot of time talking about those mitigation measures around existing buildings. Benchmarking lab performance. So really just it's a complex, you know, mix, trying to come up with predicting and reducing energy in a lab. And so really tracking and metering those buildings as much as possible really helped us identify where energy was being consumed on campus, and really helped us target those packages of mitigation measures that we could then have confidence would meet our goals. We wanted to align the goals with federal, provincial, and municipal certifications and certifications. And absolute targets was the ticket for us to do that, so we could line up exactly what needed to be achieved, and then we could also transfer that to our big, hairy, audacious goal of 37% reduction. But really trying to simplify that that design process too for design teams. And I think it's really important when you're doing an exercise like this to really test those pathways to success. You know, get comfortable with these ECM recommendations. Talk to as many stakeholders as you can about them. You know, it's easy for an energy modeler, for example, to kind of stay at your desk and to complete these models and say, oh, here's the action items to achieve your energy goals. Go for it. But when it really comes to implementing those, you need to be talking to the the design teams, the campus sustainability teams, the operations and maintenance teams, and really get everyone comfortable with a set of recommendations and packages that can be applied, and we know will meet the goals, but also can be implemented and cost out. And that's something I haven't talked much about in this conversation, but having cost consultants on board, obviously, none of this will happen unless the costing makes sense. So that was also a part of that stakeholder team that we looked at. The other kind of big lesson learned, I think, is that this, as you can see, I showed you that the bar graph showing, implementation of energy conservation measures and those for different topologies. It really got to be a fairly technical discussion. And so getting our stakeholder groups versed in that language and understanding, what it meant to have multiple archetypes performing at different percentages and doing so using different energy conservation packages. That was really, a lesson learned was to get to that point really early. So really get results in front of your stakeholder team, decision-making team as soon as you can, because we did and you do spend a lot of time working through those technical details, and the more that everyone is familiar with them, and the earlier that can happen, then the more time you can spend really iterating and improving the process and design. So I think that's, let's see here. There you go. Yeah. So that's the end of what I wanted to talk about. So I thank you for listening so patiently, I assume. And so yeah, there's my email address is there on the screen. If you do have any questions that you'd like to send to me or the project team, I'm happy to answer them. And also, I think we have 10 minutes or so right now to answer questions too. So if you do have anything, either let me see here if we have anything in the chat window.
Yeah, that's correct. So we got a few minutes here. If you've got a quick question for Joel, by all means, put it in the chat and we can address it. If it's a larger question, it requires a much larger explanation, then yes, please, we can get you in contact with Joel and he can answer that directly.
Yeah, I'm not.
Oh, so you do have one there, Joel, from Dan Curley. In the labs, you had data on equipment and lighting loads. Were these measured or based on what the mechanical and electrical engineers designed?
Yeah. So for the when we started with our existing building types, yeah, we had gone through, like I said, we chose a series of buildings that were actual buildings on campus. So we used those as our starting points, and so we used the actual lighting power densities for the lighting and that. So we wanted to start from a fairly realistic place and get to a point where we were baselining the building as best as we could. So yeah, we did.
Okay. And then we've got another one here from Octavian asking, what BEM software did you use?
So we use IES virtual environment predominantly, and that's what we used for this project too. So yeah, we found it's a both, you know, it was easy enough to create the models, the archetype models that we have a suite of those, and it's really good at putting together the energy packages and looking at some of the advanced HVAC that we were looking at, like the VRF systems and some of the complicated air change systems in the labs. It was nice to use a tool like that has those capabilities. So it was IES virtual environment is what we used.
Okay.
Yeah.
And then we got another one here from Kevin on the question and answer portion here,
Mhm.
asking if you can elaborate on the makeup of the overall project team.
Yeah, okay. Yeah, good question. So the project team, when it came to on the RWDI side, we were mostly energy sustainability engineers. So that was what we brought to the table. But the stakeholder groups that we spoke with at the University of Toronto were through their sustainability groups there and their operations teams. So we talked about, we talked to facility managers were operating these existing buildings, and the design teams that were building new construction on campus and running that. Um, we didn't talk as much to user groups as I think would have been beneficial to a process like this. So, although we talked to the facilities people that ran the buildings, we didn't talk to, some of the maybe the lab staff or the teaching staff or students who use the spaces. So there's often some more kind of nuances that can be figured out by having those conversations too. So that was one thing I think we could have improved on if we had do it again or had more time.
Perfect. Then we've got one here from Mary asking if you can elaborate on DCV for fume hoods. Are you referring
Yeah.
to monitoring and setbacks?
Yeah, again, great question. So yeah, what we're talking about there is so DCV, demand controlled ventilation. So basically, where possible, I mean, it all depends on what's going on in the lab and what you've got in that air, obviously. But when possible, to minimize your air changes, so setbacks at night in particular, if possible. So that was a big one. If we're talking 12 air changes an hour or something like that, if you can get that down to 6 or 8 air changes an hour, um, for your overnight rates, which are often doable. And that can be proven sometimes with CFD modeling or with discussions around air quality. So yeah, setbacks were a big one. You can really reduce energy consumption and the heating that goes into bringing in that air, that outside air, particularly in the cold winters of Toronto. And the demand control ventilation, those are, yeah, for fume hoods. So anytime that, we could incorporate so fume hood controls that would only be at maximum air change when in use, that really helped drive down both those fan energy and our conditioning energy uses. So setbacks and DCV for fume hoods were our two big dials there. I think you've got those right, Mary.
Okay, and we've got a follow-up from Octavian asking
Mhm.
if it was not feasible to consider geothermal HR chillers, low temperature concerns with refrigerants for VRF.
Okay. So sorry, let me see if I can read that. So that's looking at whether it is possible to incorporate geo-exchange systems with VRF, or was that a list? I didn't quite pick that up.
Looks like it was a list.
Okay. So yeah, so um, the geo-exchange, that was the carbon action plan for the university has earmarked a couple of big kind of infrastructure changes to the energy on campus, and one of those is to bring in more geo-exchange. So there's existing district energy, and then they're also moving towards geo-exchange. So they're with that, there were opportunities for low temperature circulation like you're talking about. So there's ways of, basically what we were incorporating into our models was ways of having the geo-exchange systems feeding low temperature supply on both the heating and high temperature supply, I guess, on the cooling side, and then just basically pumping up those supply temperatures with in-building systems like the VRF that you're talking about. So yeah, that was included in the model, and our projections was trying to incorporate those geo-exchange and the multiple temperature kind of setbacks that were associated with those. And that, again, like I mentioned before, was one of the reasons we chose a software system like IESVE, because yeah, we can do all that and control all that within it.
Okay, and we're gonna have time for just one or two more questions. We try to keep these things as close to an hour as we can. So we've got another one here asking if you considered Airgenuity systems for future lab DCV designs as a standard design practice.
Yeah, and yeah, sorry, I didn't mention that specifically, but that was one of the when it came to the high performance ECMs for the lab spaces themselves. It was, yeah, I took out the brand name, but it was the Aircuity systems that we were modeling basically as our solution there. So that was when it came to the high, or sorry, the mid-level mechanical solutions for the labs. It was based on that technology. I didn't want to specifically be. I took that out of the presentation actually, but that's ultimately what we used.
Okay, and then one last one here from Kevin asking, do you use schedule for wet lab setbacks?
Did we use a schedule for, yes, yeah. So that was the way that within the model, we scheduled the setbacks. So we talked a lot about, how these labs were going to be used and the occupancy requirements. And so that was all, I believe is what you're getting at, is that was all considered when we talked about reducing those night setback hours. It was all through the schedule of use. And so we reduced those air changes for periods when it wasn't going to be used or occupied as much as during the day.
Okay, and I think that is probably all we have time for today. Thank you so much, Joel, for your presentation today.
Yeah.
As a reminder to everyone here, these presentations are recorded and can be found on the SLCAN website, along with all of our past presentations if you want to catch up on something. We have a fantastic schedule coming up this year for 2021. It is almost completely booked. I look forward to seeing you guys here. It's going to be a great year for this stuff. I apologize for a little bit of the late start there and some of the technical difficulties. This is the first time we're using Zoom for this program. We'll get a little better as we move forward. And thank you so much again for everyone. If you have any further questions, please feel free to reach out to Joel or to us at SLCAN and we can direct them his way.
Thanks everyone for your time today. Appreciate it.
Thank you.
All right, take care.